As usual, we have a problem that involves the manipulation of fractions. However, we find that this kind of a problem you will find more often than the other type on the examination paper. In number 1, we do not always have fractions to manipulate in this form, but we find that the problems involving fractions are the one that we have more often than not. Before going into the manipulation of the fractions, as usual, let us convert the mixed numbers to improper fractions. There we have labeled the different parts of the mixed number. We have the whole number, we have the numerator, and we have the denominator. In converting the mixed number to an improper fraction, first we multiply the denominator of the fraction by the whole number. That we will do first. So 4 multiplied by 1 is equal to 4. Then we proceed to add the numerator to the result. So 4 plus 3 is equal to 7. So 4 times 1 is 4, plus 3 is equal to 7, and that will be the numerator of the improper fraction. And of course, the denominator is the same as before. Do the same. Denominator, multiply that by the whole number. The result is 6. To that result of 6, we add the numerator, which is 1. 6 plus 1 is equal to 7. And that is the numerator of the improper fraction. And the denominator will be the same as the denominator that we had before. So let us go straight ahead. Rewriting the expression that we have. Using the improper fractions that we obtained on the previous slide. So we have converted 1 3/4 to 7 over 4, and we have also converted 3 1/2 to 7 over 2. Squaring a fraction is the same as squaring its numerator and squaring its denominator. So whereas we have 7 over 4 squared, to achieve the squaring of the fraction, we need to square the 7 and square the 4. In the meantime, what we have done is make use of the fact that dividing by any number for that matter is the same as multiplying by its reciprocal or multiplicative inverse. So we have, of course, squaring the 7 we get 49, squaring the 4 we get 16. Then we make use of the fact that dividing by a fraction or any number for that matter is actually multiplying by its reciprocal. So we have formed the reciprocal of 7 over 2, which is 2 over 7. And of course we have squared this fraction here. And we see common factors, so we will reduce the fraction by common factors. So the fraction may be reduced by a common factor of 7, then by a common factor of 2. We have 7 into 7 is 1, and 7 into 49 is 7. Of course, 2 into 2 is 1, and 2 into 16 is 8. So 7 into 7 is 1, 7 into 49 is 7. 2 into 16 is 8, and 2 into 2 is 1. 7 multiplied by 1 is 7, and multiply 8 by 1 we get 8, and that's all there is to it. Multiply the numbers as we have said before. 7 multiplied by 1 is 7, and we do that to the denominators also. Now we'll be working with decimals. Especially in recent years, the problems that require that we find the square root may be solved without the use of the calculator. We know that because there are 4 decimal places in the number, the square root will have 2 decimal places. So if we have a particular number, especially if the number of decimal places is even, say 6 decimal places, if we find the square root of that number, then the square root should have 3 decimal places. So while taking the square root of a number, we take half of the number of decimal places. Now we have 4 decimal places right there. Taking half of 4 is 2, so the answer should have 2 decimal places. Also, because 529 is close to 625, we may say that is not so close. Well, at least for a square, they are very close if we are talking about squares, because if we square 20, we get 400. If we square 21, we get 441. That one is, as a matter of fact, 41 units away. But because they are squares, we imagine that the greater the number that we square, then the further the numbers will be apart. Therefore, if we have 529 and 625, we think that those should be relatively close to each other, being square numbers, if we are saying that 529 is a square. So they should be very close. Now, since 625 is equal to 25 squared, then 529 could be, I'm not saying that it is, could be 23 squared. Because if the squares are close, we imagine that the numbers should be close, so we are just opting for 23. Now, focusing on the 9, 3 squared may also be a good clue. So if we are thinking about the 9 at the end, squaring 3 we get 9, although squaring a number that ends with a 7 also gives a number that ends with a 9. But we are saying that we are focusing on 23. So if it is actually the square of 23, then squaring 3 to give 9 will also be a good clue. So sometimes we could take an approach where we set aside the calculator and make use of our brain. Your calculator would have revealed that the square root of 0.0529 is in fact 0.23. I hope that no one attempted to add before finding the square root. Well, it is far-fetched that anyone would want to add this number to this one and then find the square root. We don't imagine that anyone will want to do that, but stranger things have happened. Now we will do the square root first, and then when we get the result, we add 0.216 to it. And we said that the square root of 0.0529, we could imagine without using the calculator that it is actually 0.23. But these days, CXC examiners imagine that students have the calculators at their fingertips, so they expect that students will use them. So we have 0.23 plus 0.216. And that may be done in our minds without the use of a calculator. As a matter of fact, we realize that if we align the decimal places, although we're not doing that physically, but mentally we should be able to handle problems like these. If we align the decimal places, there will be no decimal place that is in line with the 6. It will go back, so we have a 6 there. So on the alignment of the decimal places, we realize that there is nothing that will be aligned with the 6. It will go right back, and we see that 1 plus 3 will be 4, and 2 plus 2 is 4, so 0.446, like that. It is required that the answer be finally written in standard form. There should be one non-zero digit to the left of the decimal point. By so doing, the number will be increased by 1 decimal place, or multiplied by 10. An adjustment will have to be made that will return the number to its initial value. We therefore divide by 10, which is equivalent to multiplying by 10 to the negative 1. So there we have it. Now we have this number 0.446. To write this in standard form requires that the decimal point will be here instead of here. By so doing, it means that we will be multiplying or increasing the number by 1 place of decimal. So we are increasing its value by 1 place of decimal, which is the same thing as multiplying by 10. Now we cannot just leave the number multiplied by 10. We have to bring it to its original value. So if we multiply by 10, to bring it back to its original value, we'll have to divide by 10. Dividing by 10 is the same as multiplying by 10 to the power of negative 1, and hence what we have right here. We may consider that making a small number larger will have to be compensated by making it small again. Therefore, any number that initially had 0 preceding the decimal point will be accompanied by a negative power of 10 in the end. The power of 10 will be determined by the number of decimal places by which it was increased. Therefore, if we have a small number, what we call a small number is a number with no non-zero digit preceding it. Therefore, any number that has 0 point something, we will consider that to be a small number. In the end, that number will have to be accompanied by a negative power of 10, because having 0 here means that we can only, by writing it in standard form, increase its value. Therefore, we will have to decrease its value again. So if we have no non-zero digit preceding the decimal point, we imagine that in the end we will have our number accompanied by a negative power of 10, and the power is determined by the number of decimal places that we increase the initial number by. Now we are given this problem in which the hourly rate of pay is $22.50, and we are talking about a 40 hours work week, and we need to find the weekly wage, and that will be done by, of course, multiplying the number of hours by how much is worked in a particular hour, and that is a simple result. $22.50 multiplied by 40 is equal to 900. As a matter of fact, 22 times 40 is equal to 880, and a half, so we have 0.5, which is a half. A half of 40 is 20, so we have 880 plus 20, and that will give us 900. So that is also something that we could have done mentally. 1.5 times the hourly rate may be taken at face value. We always associate times with multiplication. So for 1 hour of overtime, we multiply the hourly rate by 1.5. So we just need to determine the overtime rate, which is the overtime hourly rate, and it is 1.5 times. So multiply 1.5 times the hourly rate. So we have $22.50 multiplied by 1.5, which is 1.5, and this is the hourly rate, and this is the hourly rate for overtime work. We are told that the number of hours worked in a particular week is 52, and we need to know her wage for that particular week. What does that mean? If she is working 52 hours, that means she should be working a certain number of hours more than the regular working hours, because the regular working hours is 40 hours. Therefore, if she is working 52 hours, she is somewhat over that. Now we need to determine, because we just cannot go straight ahead and do all the calculations together, we have to consider that there's a particular rate, which is a different rate for regular hour as opposed to overtime hours. So we need to separate the regular time from the overtime, and we have 40 hours for regular time, so the overtime will be the difference between the regular hours and the total number of hours. 52 is the number of hours that she worked, and 40 is the number of regular hours. The difference between that will be the overtime hours. So 52 minus 40 is equal to 12. So that will be the number of hours that she worked overtime. The number of hours that we have calculated for the overtime will be multiplied by the overtime rate. And of course, we know that the regular wage for the week is what we have right here, is $900. So those $900 will represent all of the hours that she worked regularly, and then we'll add the overtime, which is 12 multiplied by the overtime rate. We'll add that to it. So there we have $900 plus 12 times the number of hours, that is 12 multiplied by the overtime rate, and that gives $1,305. In order to find the number of hours that she would need to work in order to earn $1,440, we need to subtract the regular weekly wage from that amount in order to determine the amount that she would earn in overtime wages. Then divide that amount by the hourly overtime rate. So we have 1,440. We will take away the regular wage from that, and then divide this value by the overtime rate and see what happens. So that turns out to be 16 hours. So we have 1,440, which is the amount of money that she needs to work. We subtract the regular salary, and with that result we divide by the overtime rate, and that turns out to be 16 hours. What we could have done also, we could have found the difference between this and the 1,440. Then we would divide that by $33.75, and after doing that, the result would turn out to be just 4 hours. Therefore, with the 12, the 4 hours will turn out to be 16 hours. So we could have taken that approach also. There we have a system of simultaneous equations. Examiners have a way to play hide and seek with simultaneous equations. There is usually a simpler way out than what we would capture at first glance. Taking a second look at the system will reveal that the coefficients of y are additive inverses. They have different signs but are the same in value. Adding them will result in 0. We may therefore go ahead and add the two equations. eliminating the y's. So we have a positive 2 here and we have a negative 2 there. If we add them together, the result is 0. We may go straight ahead and add the two equations. I am sure that some students will see it a little bit simple also, not simpler, will see it simple to just multiply this equation by 3 and then find the difference, which may be simpler than what we would expect, but they're simpler still, with the coefficients of y being additive inverses. So we add the two equations and the y's are eliminated. 3x plus x is 4x, and 13 plus a negative 1, which is 13 minus 1, is equal to 12. We have 4x and 12. Dividing the equations by 4, the x will be the only thing left on the left hand side. The 4 will be eliminated, and 12 divided by 4 is equal to 3. So x is equal to 3. Take that result, which is x is equal to 3, and substitute that into equation 1. So in equation 1, where we see x, we replace that with 3. And then, of course, we have 2y and then 13. So we have 3 times x, which is x is 3. So 3 times 3 plus 2y is equal to 13. And of course, 3 times 3 is equal to 9. So we have 2y is equal to 13 minus 9. So 2y is equal to 4. And y is equal to 2, dividing through this equation by 2. So x is equal to 3 and y is equal to 2. As in all cases, when solving a pair of simultaneous equations, we may eliminate either the x's or the y's. We should progress, making use of any loop of simplicity that exists. Whenever we are manipulating positive and negative numbers, it is always easier to add than to subtract. Making use of additive inverses when they exist or are easily created is usually a simpler route. So making use of additive inverses, I always try to do that if it is an easier way out. If we see additive inverses, then we make use of them. If they are easily created, then we create them and then we move straight ahead. But we always try to make use of any what we call loop of simplicity that exists. Although it might not be so in all cases, examiners more often than not make it at least a little more time consuming to eliminate the x's than the y's. This technique is for candidates who are programmed to invariably eliminate the x's. Do not forget that 2 takes longer than 5. It is better to take an extra 5 seconds to examine a pair of simultaneous equations than an extra 2 minutes to solve it. So a system of simultaneous equations, it is better for you to take an extra 5 seconds to examine the system than to take an extra 2 minutes to solve it. Now we are about to factorize completely, and this first expression to be factorized is in the form of a difference of two squares, everybody's favorite. It is required to be factorized at sight. Usually we imagine that it attracts only a single mark in the examination, factorizing a difference of two squares. Therefore we do not imagine that it should take 3 steps in entirety. So there we have it. X squared is the square of x. X occupies the first position in both pairs of brackets. So we have x there and we have x there. Also, we need to know what we square to give 16. 16 is the square of 4. 4 will occupy the second position. And in the end, we will place a negative sign in one bracket and a positive sign in the other. And the order does not matter. That is, if we put plus here and negative here, or put negative here and plus there, then it will not matter, as long as the two signs are not the same. And that is our answer. Now we have our expression, 4 terms. We will use factorization by grouping. So for this expression, we may factorize in pairs, then factorize the expression as a whole. So we have that, which is, as a matter of fact, being a little bit elaborate, because it is not completely necessary to include this intermediate step, but I'm just including these steps. We'll have another one in order to make the process clearer. So we are actually taking the common factor of x, and then we are dividing each term by the common factor. So the common factor, what is common in 2x squared and 3x? X is common, so we take the x here, and 2x squared we divide by x, and also 3x we divide by x. Also, what is common in 8x and 12? 4 is common. Generally, we take the highest common factor because we are in the habit of factorizing completely, and that can only be achieved if we take the highest common factor. And we say now 4 into 8x there, so 8x divided by 4, and also we take the 12 and we divide that by 4, and that is the result. So we have 2x squared divided by x is 2x, 3x, the x is cancelled, 8x divided by 4, 4 into 8 is 2, and there's nothing else. Then we say 12 divided by 4 is 3. Right. And there we have common factors again. So we will take the common factor and then divide by the common factor. So we will factorize a bit further by taking a common factor of 2x minus 3. So we have x, 2x minus 3 right there, and we divide that by 2x minus 3. Then we have 4, 2x minus 3, we have it here, then we divide by 2x minus 3. So we take the common factor and we divide each term by the common factor. Of course, these will eliminate each other, and we have x. These will eliminate each other, and we have 4. So we have 2x minus 3 and x plus 4. And that's all there is to it. So we have a total of 28 tickets. X were for adults, and the number of tickets for children must be the remainder. So X were for adults. So what do we imagine? If we have 28 tickets, X were for adults, then what do we imagine? If we have 28 tickets and we have 8 of them for adults, how many will be for children? We just take away the 8 from the 28. It is the same thing here. If X were for adults, then what will remain? 28 minus X for children. The amount spent on adult tickets must be equal to the cost of each ticket, which is $30, multiplied by the number of them. So you take the number of them and multiply by the cost of each one. That's not very difficult. So 30 multiplied by X. And what about for the children? The same applies here as in Roman 1b above. The amount spent on tickets for children is equal to the cost of each one, which is $15, and we multiply that by the number of them, which is 28 minus X. So we take the cost of each one, which is $15, and that we multiply by the number of them, which is 28 minus X. So 15 multiplied by 28 minus X. The total spent on tickets must be the sum spent on adults tickets added to the sum spent on children tickets. The total will be the amount spent on adults tickets and add that to the amount spent on children. There we have it. And we are required to simplify that expression. So we take that 15 and we multiply that by 28. When I'm required to do something like that, I can do it mentally. I usually say 15 and treat it as 1.5. So we say 1.5 times 28. 28 is 28. A half of 28 is 14. 28 plus 14 is 42. But do not forget that it is not multiplied by 1.5. It is multiplied by 15. Therefore, it is not 42 but 420. And of course, 15 multiplied by x is 15x. And this will return as it is. I can imagine before the next step we realize that negative 15 plus 30, which is of course 30 minus 15 is 15. So in the end we should have 15x plus 420 or 420 plus 15x. And that is the amount spent overall. To find the number of adult tickets, which is x, as we have it right up here, to find the number of adult tickets, we may equate the expression, which is the one that we have arrived at right here, that expression in x, we may equate that expression in x for the total number of tickets, right, and that we will equate to the known amount of money spent on those tickets. Of course, that is given to us in the statement of the problem. So we equate the expression for the total number of tickets that contains x to the known amount of money spent, and we'll be able to find x there. Of course, we will eliminate this 420 first by subtracting 420 from both sides, in which case from the left hand side 420 will be eliminated, and here we have 660 minus 420, and that will be 240. There we have it. And that is equal to 16. Sometimes I like to exercise my brain, especially when I see a number like 15. X is equal to 240. I'm saying to myself, what number do you take 1.5 times, because 1.5 is related to 15 and the result is 24? Then it is easy to see that it is 16, because half of 16 is 8. 8 plus 16 is 24. So I can do that mentally and say x is equal to 16. Nice. Here we have our problem involving sets. The set A contains the odd number members of the universal set. Odd numbers are not divisible by 2. They are the numbers that end with 1, 3, 5, 7, and 9. So let us write down the set A. But the set A of odd numbers must be of the odd numbers that are in the universal set. So write down those odd numbers. 51, 53, 55, 57, 59. Those are the odd numbers. B contains the prime numbers. They are contained in U. The only even prime number is 2. So since 2 is not in this universal set, all of the elements in the set of prime numbers will be odd. So if all of those prime numbers will also be odd, then the set of odd numbers must contain the set of prime numbers. Or we may say that the set of prime numbers must be contained in the set of odd numbers. Right. the only even prime number is 2 and it is not there. So all of the prime numbers must also be odd. The 50s contains at least 2 numbers that look like prime numbers but are not. They are 51 and 57. 55 also is not a prime number. Let us write down the members of the set B. Of course, 55 does not look like a prime number at all. Right, so let us write down B. B, 53 and 59 alone. We are saying that 51 is not a prime number, 55 does not look like one, and also 57 is not a prime number. So only prime numbers are 53 and 59. So 53, 59. Those are the prime numbers. In completing the Venn diagram, we have to consider that since all prime numbers apart from 2 are odd, that the set of prime numbers must be contained in the set of odd numbers, since they will all be odd. Begin by placing the members of B first. So we have the two sets. B is required to be inside of A, because all prime numbers between 50 and 60 are also odd. So they are required to be in the set of odd numbers. Put in the set of prime numbers first. So the first prime number is 53 and the other one is 59. We do not have any other. So the other odd numbers will be outside of B but inside of A. 51 is inside of A. 55 is inside of A. 57 is inside of A. They are not inside of B though. The even numbers will be in the universal set only. So the even numbers will be 52 right there in the universal set only, 54, 56, 58, and that's all there is to it. As stated before, apart from 2, all other prime numbers are odd. Therefore, considering the universal set, the prime numbers must be taken from among the odd numbers. 51 is not a prime number. If there is a number whose digits have a sum of 3, then that number is a multiple of 3. So that's a rule of thumb. 5 plus 1 is equal to 6. Therefore, 51 is not a prime number because 6 is a multiple of 3. So 6 is a multiple of 3. Therefore, 51 is also a multiple of 3. The same thing applies for 57. When we add 5 plus 7, we get 12. Since 12 is a multiple of 3, so is 57. So 12 is a multiple of 3. Therefore, 57 is also a multiple of 3. 57 is therefore not a prime number. 55 is more obviously not a prime number. The double 5 tells us that it is a multiple of 11. Also, it ends with a 5, indicating that it is divisible by 5. So finally, prime numbers are numbers that are only divisible by themselves and 1. Let us look at the factors of the numbers. So 51 has factors of 1, 3, 7 and 51, which is more than itself and 1. And 57 has factors 1, 3, 19 and 57. 55 has factors 1, 5, 11 and 55. They usually have more than 2 factors. They are therefore not prime numbers. Our first step in constructing the triangle is to draw the line DE, which is equal to 10 centimeters. Of course, we are constructing a triangle and we are doing that to particular specifications. So the first step is draw DE 10 centimeters. With the aid of the ruler, draw a line 10 centimeters long as shown. So there is our ruler, and we will start there and end down the road 10 centimeters, or of course 100 millimeters. Let us label those points at the end of a line DE. CDE is 45 degrees. So this angle, which is CDE, that should be located at the middle letter, therefore it should be located at D. So the 45 degrees angle, the angle is located at the middle letter, which is D. So let us therefore construct that angle at D. The process will not be carried out, only the constructs will be shown. And what does the construct represent? This here, we have this large portion here, is our 90 degrees construct. And of course we have the construct, which is the rest of it over here, which is the construct that we use to bisect the angle. So in forming a 45 degrees angle, we construct a 90 degrees angle first, then we bisect it. Half of 90 is 45, that's all. So in this case, only the construction lines are shown. DC is 8 centimeters. That's what it said. DC is 8 centimeters. So what do we do? Draw DC from D through the 45 degrees arcs. So here marks the 45 degrees. So draw from D through these arcs all the way a distance of 8 centimeters, and there we will locate the point C. Where is that point C? I hope it is somewhere near. Well, we do not have it yet, but maybe by the completion of the triangle we will have it included. There it is. So complete the triangle, and there we will have our point C. In order to construct CF perpendicular to DE and meet DE at F, we will proceed as if we are constructing a kite whose diagonals are perpendicular to each other. CF will be a part of the diagonal. So we are trying to complete a kite by getting this line to be down here and this one down here also. So in a kite we have these two adjacent sides equal in length and these two adjacent sides equal in length. And because of that construct, then the diagonal that goes from C all the way to the other side over here will actually turn out to be perpendicular to this one, as we generally have in a kite. So in order to do that construct, what do we do? Place the point of the compass at D. So put the compass point here and open it in such a way that the point of the pencil is at C. So we put the point of the compass here, open to C. What does that achieve? We are trying to get the same length as DC down here. So there's our arc. And we need to get the same length as CE over this side also. So we'll put the compass point at E, then open the compass to C in such a way that the pencil is at C and the point of the compass is at E, and then we make an arc to cross this one. So what will happen is that this line will be equal to where it goes across here, and then this one will be equal to this one there. So let us make that arc right. We will not complete the kite because it's not a necessity. All we need to do is draw the line right here, 90 degrees. But we are saying the idea of getting it done is to consider that the kite will have diagonals that are perpendicular, and if we can create the frame of that kite, then we are sure to get this line that goes from C to F that we have not yet placed here will be perpendicular to this line. The line from C to its intersection of the arcs will be perpendicular to CD. Where it intersects CD is the point F. So we finish by drawing the line CF. right? So we imagine that for the kite, this diagonal is perpendicular to this one, but we do not need the entire diagonal. We just need to have the line CF, which will end right there. To measure the angle DCE, that's the angle that we need to measure. Place the center of the protractor at C and use DC as the zero line. Although we could put the center of the protractor at C and use CE as the zero line, because we want one of these lines to be on the zero line, and then we measure the angle maybe in that direction. This line will be the zero line. We measure the angle in this direction. So any one will do. But in this particular case, we are saying put the center of the protractor at C and use DC as the zero line, like so. What do? We take note of where this line intersects the scale. So we are taking a look at where the line CE is tipping on the scale right here. And then that, because this point here, this line is our zero line. So the angle goes all the way around here and increases in this direction to right here. And we'll take note here of what the angle turns out to be. Let us see, we have about, for sure, 80, 1, 2, 3, about 84, maybe 85. So DCE is 84 degrees. The angle obtained here is a bit different from the one obtained on paper. Paper provides a more accurate device to work with. Apart from that, even candidates who are all working on paper will get answers that vary a bit. So all students will not necessarily get exactly 81 if the answer is 81. Some might get 80, some will get 82, maybe 83, and so on. So, as a matter of fact, there is no such thing as a perfect construct. So we imagine that it might be a little bit off sometimes.